So with that, I'm going to hand over now to Dr. Feltman, and then we'll return back at the end.
Thank you. Hi, everyone. So starting in our mission here, it's midnight, and our pilots have woken up for this crucial mission. It's still dark out. That makes it difficult to wake up. Waking up at midnight is difficult. And becoming alert to the level that they need to perform this crucial mission is also difficult for the pilots to obtain if they haven't received an adequate amount of sleep, if they had uncomfortable sleeping quarters, if there's a lot of environmental noise. And further compounding their fatigue are circadian rhythm differences. And so some individuals are able to wake up at odd hours of the night and perform at their optimal alertness and performance levels, while others struggle to become alert. And so those who are fatigued and not alert are at an increased risk for making the errors that can cause mishaps. And so, oops, actually, I jumped ahead. To avoid the detrimental effects of fatigues, we are evaluating how differences in circadian rhythm can impact mission performance so that we can develop fatigue mitigation approaches that are tailored to the individual soldier and to provide leaders with the tools that they need to make our soldiers able to perform at their optimal levels. So moving on in our mission, it's 0100 hours, and our soldiers are gearing up for their flight. And in our future scenario, this now includes putting on flight gear that has biometric sensors embedded. This can include an electrode that's built into their helmet, some respiration and heart rate monitoring sensors that are built into their tops. And it can also include small cameras that are built into the cockpit that monitors their eyes, their eye movement, and their pupillary changes. To make this possible, our team of researchers is examining several different types of sensor technologies. So we're looking at physiological monitoring of the brain activity, the eye activity, our respiration, our heart rate, just to name a few. We're doing this because we know that wearable technology is everywhere and it's becoming less invasive. So our studies will be able to determine what sensors our soldiers need to wear and what sensors are needed to identify the cognitive changes that may impede mission success. So through these studies, we will be able to provide the data that is needed to develop the algorithms for predicting performance changes and develop a standardized objective metric for assessing the impact of new technology on a soldier's performance. So this metric could then be integrated into the acquisition cycle to ensure that the systems we're trying to implement in the cockpit or the grounds vehicles are actually able to help our human soldier that's working with that machine and not hindering them from their ability to operate. And moving on to 0130 hours, our pilots have taken off, and now in our future scenario, they're having to coordinate not only with other manned aircraft, but also other unmanned systems. So this means that they will now have increased information coming from multiple channels that they'll need to be able to integrate and make decisions based on, as well as fly and maintain their situational awareness. To successfully handle the increased information or the increased flow of information and maintain situational awareness to keep them safe, our soldiers will need to be able to divert their attention to different sources of mission input. To help our soldiers successfully integrate mission essential information so that they can make the decisions that are required, we are examining how non-invasive brain stimulation and pharmaceuticals can enhance their ability to attend to different sources of information, increase the speed at which they can process that information, and make quick but accurate decisions using all of those sources of information. These will then be used in healthy soldiers to enhance their operational effectiveness before they go on a mission, as well as to avert operator overload when it's detected by biometric sensors during the mission. So moving on in our mission, our pilots have been flying for several hours, and they're now at the critical point in the mission. Their alertness is an absolute necessity to ensure a successful mission, but it's becoming difficult to maintain as they're now assuming control of autonomous vehicles, as well as responding to and monitoring video feeds of those ahead of them. We do not currently have an objective means to detect when an operator's performance is slipping in real time, and so the biometric work that our team is doing will enable the detection of when the operator is becoming overloaded, and we'll be able to do that in real time. This will allow us to engage an adaptive automation system that will ensure that the human and the machine are working in a balanced manner so that the human stays engaged in the mission but does not become critically overwhelmed. And so we are evaluating the impact of different sources of workload that our operators will encounter, such as cluttered visual displays or increased auditory feeds. And we're using this to develop a suite of sensors that are most sensitive to identifying overload within those different sources and to aid in the determination of which tasks need to be offloaded to the machine in order to maintain our operators' effectiveness. And so to show a quick example of how we are able to monitor brain activity in near real time, we have this clip from a recent study that we completed. And so in the lower left box is what the pilot saw while they were flying, and the lower right-hand video is what the out-the-window view was. The upper left demonstrates how algorithms using the pilot's brain activity that we measured during the flight can be used to identify changes in their workload. And so the yellow line with spikes upward is showing an increased level of workload experienced. And then the far right is a heat map showing how his brain activity was changing during the flight. We're most interested in increased activity in the frontal lobes. And so you might watch that and think, so what? It looks kind of cool, but what's the outcome of this? Well, as we continue collecting this type of data, we can use the numbers that are driving the changes in those lines on the graph to then predict when the automation needs to take control and use that to avoid a mishap instead of waiting until a mishap is likely to engage an automated system. And so finally, our pilots are at their last leg of the mission. It's 8:30. They've returned to friendly territory, but they've been flying for about 7 hours under some pretty stressful circumstances. And they're now at risk for being fatigued and becoming complacent. And in fact, we know that a significant number of mishaps tend to happen during this time. And within these sorts of circumstances where someone's fatigued and likely to become complacent. And there currently is no validated method for detecting states of inattention in real time, yet we know it's a threat to our aviators, to our UAS operators, and even to our grounds troops. And so the detection of these states is critical to ensure safe mission completion. We will be completing work where we induce this state in soldiers and measure their physiological response with our biometric sensors. This will help us to create a validated and reliable method to detect inattention and enable the machine to then shift controls back to the human instead of away from the human to allow the human operator to stay engaged and situationally aware of the mission that they are completing. So those are just a few examples of the ongoing work that our team of researchers are completing to help our soldiers in the future battle space. And I will now turn it back over to Colonel Taylor for a couple of closing remarks.
Thank you, Dr. Feltman. I think we can all appreciate how important that work is as we particularly move to these autonomous, blended autonomy, variably autonomous platforms, right? They need to know when they need to help you out, and you need to know when you need to take control back from them. And this is the foundational work, we think, that helps us understand when the machine needs to help the man and when the man can then take back over from the machine. So we see this application, directly translating into programs like Future Vertical Lift, the Next Generation Combat Vehicle. We even think that there's going to be applications as soldier lethality, as ground soldier systems become more and more complicated. For the trivia question, who owns most of the UAS platforms in the DoD? The United States Army, actually. Between those three programs, Eagle, Raven, and Shadow, we actually now have more unmanned platforms and systems than any of the other services. So there will be a lot more UAS operators currently now in the Army than there will be in the other services. So with that, I think I'd like to wrap up and then see if there's any questions. I do appreciate your time and attention today. It's been a privilege to represent not only the USAARL Laboratory, but also to represent MRMC today, and open the floor to any questions. Yes, sir.
Do you acquire and analyze very large databases as part of this work? Is that?
Yes,
Can
sir.
you describe a little bit about what that looks like?
So Dr. Feltman is probably better qualified to answer that, but you can imagine that a single experiment actually generates enormous amounts of data. So that enormous amount of data taken over multiple subjects, over multiple projects, over multiple years, we actually have a very extensive database. Certainly one of the things we're trying to understand as we move into the modern era is how do we apply deep learning, how do we apply learning algorithms, data management, how do we do those things well so that we actually can mine not only the data that we have collected, but actually data that's been collected previously that we happen to store and use that in a way that helps us, right? We know that, by other work, that you can take a machine learning algorithm and show it thousands of pictures, right? As we have a dermatologist in the field, you can show them thousands and thousands of images, and the machine can actually start to detect basal cells about as well as a human being, or with radiologic images can do the same. It can start to detect very fine. So we also believe that there's a lot of great things that can be detected in this data. So in the next 6 to 12 months, we are looking to see how we can begin to apply that sort of machine learning to the data that we do have. Any other questions? Again, if nothing else, I'll be standing around. We'll be back at our booth if you'd like a further demonstration. But again, on behalf of General Holcomb and Command Sergeant Major Rogers and General West, who's also joined us here today, the current Surgeon General, we'd just like to thank you for the opportunity to present today. Thank you for your attention, and we'll be happy to answer any questions you have. So, thank you.